Okay, hi there. My name is Joachim. I'm going to talk about a project called CrypTech, which is and then the Open Hardware Security Module platform. And just starting, this is me, Joachim Strömbergson. I am an IT security consultant working for a company called Assured. I specialize in embedded systems, ASIC and FPGAs, and biometrics. I also work a lot with crypto. And I don't mean blockchain in that case. In my copy's free time, I write a lot of open crypto hardware implementations. So if you go to my on GitHub, for example, you can download a lot of cores that are done for AES and a lot of other crypto stuff. And I do like to work on CPU designs and assembly hacking. Many years ago, I was part of a team called Fairlight. If you maybe heard about that. And someday I'm probably going to try to release another demo or something like that in any year. But I'm going to talk about hardware security modules and what they are. We start with what they are and why they're important and why we see there's a problem of them being black boxes. So a hardware security module is a dedicated appliance, a device that is used to generate and store secrets, typically private keys, and protect them inside the machine, and basically offloading sensitive operations from a general system to your normal PC to perform operations with these keys. And these hardware security modules, HSMs, they are very expensive, easily cost you $100,000 if you want one. There are very few vendors. If I say there's a handful of them, I probably have one finger too many. They're quite big national interests in these devices. They're often connected to organizations that like secrets, like NSA, for example. If you look at the Encipher, one of the vendors that used to be around before they were bought up and was started by NSA people, for example. And today, basically all of the HSM vendors are owned by Dassault, the French defense manufacturer. And an HSM, as I said, it basically looks like this. You have something like a CPU inside the machine that they can do, that can perform operations, and it also has hardware acceleration for crypto, typically RSA operations, AES, DES, triple DES, asymmetric operations. And then you have a storage of secrets inside the machine in a database, typically flash memory. And then, very important key part of it is a random number generator, a high quality random number generator that can generate keys that you can actually know and trust, And these machines, there are a few standards for having to actually write applications that will talk and use an HSM. And the standard one is PCBs 11. And also there's a sort of a management interface also. So you can typically do things like, okay, I want to actually, when you install a machine like this, you actually set it up in the operation mode, and then basically enables a lot of security features. And the reason why these machines are so important is because they're used in a lot of applications. Normally if you buy a certificate, for example, you have a certificate authority, they use HSMs to do the designing operations and create to stamp the certificate, and their private keys are stored inside of HSMs. But you also have ID cards, citizen ID cards, for example, where you have basically a client certificate. It's generated by an HSM or an HSM inside of the card. And then use it for like IPsec, for example, and lottery tickets. And even the PIN code, when you get a new smart card from your bank, and you get a PIN code like 4 or 6 digits, that number is actually generated by an HSM, and then generates an envelope and sends it to you. So HSMs are used in a lot of important infrastructure and systems around the world that we rely and trust on, not least the internet, and the basis of the internet and the security of the internet. And there's this. You have this PCBs 11, and you have a lot of standards around this, formal standards. You have government agencies that write standards for for the security of these devices and how to evaluate them. There's a called common criteria, which is a standard for how to evaluate a different type of product, like an Excel, for example. And NIST, the American standards organization, they have a series of standards, like FIPS 140-2 or 100-3, to actually say there, that specifies, among things, the security levels that you have, from 1 to 4, and 4 being, that means that if somebody tries to open up your HSM for some reason, it should immediately zeroize the secret keys stored inside of it. And depending on what level of security needs, you also need to specify what immediate actually means. Is it milliseconds, microseconds, nanoseconds, so on. And then there's standards also for random number generations and how to test them. And so you typically see this EL evaluation and EL certification, and you have NIST and FEMA and validators and that. So, and all this is basically to be able to you buy this box, you can't open it up, because if you do, it will actually destroy itself. But because you have a lot of agencies and governments, and they do formal verification of this, and everything is very, very organized, then you should be able to trust these machines. And they come in different sizes and prices, of course. And typically, as I said, these are very expensive machines, but you have them either like something you can put in a rack. They can often be a card you put inside a host computer, and performance acceleration and storage inside of that. And you can note that there's actually a supercapacitor, but normally either a battery or a capacitor. So even if you turn off the host, the card itself, or particularly the tamper detection mechanism and the keys, are actually kept alive inside the machine, even if you turn off the whole machine. So the card will still be alive partially on it. And this right down here, the NXP, something that's actually what's inside your smart card. That's a secure element. It's a very, very small chip with something like 5-6 connectors on it. And it's normally not that big. It's actually shaped down, like a flat into a card. But it basically has the same mechanism as an HSM has. One of the things that actually is an 8 and 16-bit CPU inside it that runs a version of Java called Java card. So you actually write applets running on top of these cards. So it could be interesting to know that you have actually Java running in your pocket. And if you try to open up one of these guys, and this is one of the old cards. It's an IBM 4758, typical PCI card that was sold for like $15,000. And you can see there's this metal box there. And if you try to pull it apart, you can see that the wire is going inside on the back side. It's hard to get to. And actually, if you pull it off, there's actually a spring that actually one of the detection mechanisms. So it'll actually destroy itself if you do this already. And then if you try to open up and go into that actual metal part, you see this black tarry thing. It's called potting, that you actually fill everything in. But you can also start to see these layers of wires going back and forth. And it's multiple layers of electrical plastic, basically. So you can actually detect that you try to puncture a needle or something through that. It will actually detect that very easily. And then, of course, kill everything inside of it. And if you get everything off, you can actually see that, okay, it's just basically standard x86 AMD CPU. It has some small lattice FPGAs and some sort of ASIC doing some weird thing. So it's a pretty standard electronics, but it's packaged in a very secure way, so you're actually not be able to know what's inside of it. And you sort of have to trust that it actually does what it's supposed to do. And the problem is that they actually don't do that. This is an example. This is from Taiwan, and these cards would get it's a typical client certificate. So you have a RSA key pair with a private key. And what they did was that this is Daniel Bernstein, that they collected a lot of the public keys and looked at the public keys and see if they actually had public keys that actually matched, which means that the private keys also match. And they figured out that 7% of the keys were actually the same. So something went wrong with the key generation in that one. And then, of course, you had one of these guys. These are, okay, this is a token generator, but it's by the company RSA, and they implemented a random number generator called dual DNSSEC, which is one of the random number generators that is supposed to be implemented inside an HSM. But you can't actually know if your HSM is running the dual DNSSEC or not. So you have to sort of trust that the implement is. It normally says it implements SP 800-19 as a standard for random number generation, because that's required by the FIPS 140-2 standard, but it doesn't have to say which one of them. So you can actually have one of these inside of you, and it will actually generate random numbers and particularly generate keys that is backdoored, that actually I can figure out what actually it was supposed to be. And then the Taiwanese problem, because a problem doesn't come alone, it actually happened again, but with another vendor, in this case Infineon, and something like 1 billion devices had faulty RSA key generation in those. So they had to replace card or update card. And this is the good thing with having Java inside your card. You can actually send a secure applet to it and actually update your card with a new applet. But that was 800,000 cards in that update. And then, of course, you can have, if you search for CV databases, you can find some really nice problems. Like remote key export restriction bypass. One of the key things with HSM is that you're never ever going to have your CSL keys leaving the machine in an uncontrolled way. So that is basically killing that product. And arbitrary sign and key extract is also. So, given this, we have these boxes. We're supposed to trust them, but they really are black boxes. If I try to figure out how my box works, it will actually kill itself. So it's really trust at face value. So there were some people, particularly at IETF, a few years ago, that thought that this is not really a good setup and a good way forward, particularly when we started deploying things like DNSSEC and RPKI and other, when the infrastructure of the internet that we actually rely and trust on, and the basic foundation of the internet is getting based on public key solutions to provide security. Then we really need to be able to trust that those keys actually are generated in a good way, and then we can trust the HSMs. So they basically started this project to sort of develop, try to see if we can develop an open HSM that we can actually have somebody manufacture. You can manufacture yourself, but you can be able to take the components, the software design, the hardware design, the PCB design, and make your own HSM or have somebody do it for you. And also be able to sort of pick the parts that you actually need for a solution. And we didn't really know if it was going to be possible to do this. And one thing that we learned is that it's sort of a process that we're sort of moving towards a open solution. But we are a core team. We are trying to be diverse. We try to have people from all over the world. We have people from Sweden, Russia, USA, Germany, Japan, Ireland, and we try to get people from China, for example. We try to work in an open development environment to be as open as we can when we do, when we have discussions and things. And we use Git, and one thing that we do is we sign all our Git commits, so you can always trace back all the changes I've done to me. Speaking of openness, we use 2-clause BSD license for all the source files, that is all the software and FPGA source code. And so all the cores that we have for hardware acceleration of crypto stuff, like AES and SHA-256 and RSA and elliptic curve stuff, is all BSD 2-clause license. And doesn't really work for drawings as much, so we use Creative Commons instead for PCB layout and things like bill of material with all the components that we use and stuff. So you can go to, if you want to look at the track, then you can go to our track site, and then you can look at all the mailings and stuff like that. And we sort of try to work step by step towards an open tool chain and dependent builds when we build our system. So that's sort of the goal, because that's part of the trust. That yes, we do releases of binaries that we generate for our hardware, but you should of course be able to recreate them at least to see that you actually get the same binary. In terms of language, we use Verilog as a hardware description language for the FPGA cores. Use C and Python, for example, to do the modeling, to actually know that when building is going to work. Icarus Verilog is a really good, nice, open Verilog simulator that I use a lot. Verilator, same thing, a little bit harder to use. I use it mainly for linting the code. It's really good to have more than one parser of your source code. They would tend to find different problems. And of course, we are embedded software, project basically. So we use C, standard C, assembly, a lot of Python, Bash, makefiles of course. So we were kind of old school, not as much Rust and JavaScript and those cool kids. But we use an OpenOCD for debugging and GB and stuff like that. So we're kind of typical embedded project basically. And when we started out doing this, we realized that we need to start working on the FPGA design quite early and start working on the cores. So we basically got cheap FPGA boards. This is a really nice one from DNSSEC, really tiny board. And we could start doing the development of some of the key parts, like the random number generator. But it's not a very open platform. DNSSEC has really good documentation, but there's not like a PCB design or boom, and particularly it's not source code stuff for the stuff. And of course we had to use like the Intel Altera tools, like Quarters for example. A key thing for us was this. Bunny Huang released basically the first open laptop, the Nalina. It's an ARM-based quad-core CPU inside of it. It's block-free, not like the Raspberry Pi or something like that. It's really you can build everything from the single bit from booting up and all the way up. It is a very, very hacker-friendly board, so it's a huge number of interfaces. This is a few laptops that you can buy that has dual Ethernet interfaces, CAN interface, and all kinds of things. You can look at it. So it's a lot of peripherals. And one thing for us was that it was actually sporting a fairly big FPGA that is tightly connected to the CPU. So that we can start developing our software on the CPU, and then we can actually put our cores inside of the FPGA and use them as co-processors. So look at the board here, and you have the first red circuit. That's the FPGA, and then the one in the heatsink above that. That's the quad-core CPU, and then all over the edge there's a connector, and that one goes straight into the FPGA. It's a wide connector with I think like 32 or even 64-bit wide bus going straight into FPGA. So you can mount stuff on that and do quite a good high performance transfer data back and forth. And then what we did was we started developing like the noise board. We have a random number generator. A real random number generator in an HSM is based on you base hardware-based random noise. And in this case, we have basically two random noise generators, one inside of the FPGA and one outside of it. And then we started developing the one on the outside. You can see the progression of the boards we did, and the two boards in the middle and right actually has the same connector on the Nalina, so we can mount it on the Nalina, and we can start actually using it for developing the rest of the random number generator. And our RNG looks basically like this. We have the external generator. We have an entry provider that collects data from that external board. We also have an internal provider. It's based on free-running ring oscillators, digital ring oscillators inside of the FPGA. So it's working on different mechanism than the one from the outside. So if you're going to try to add bias or try to sort of modify and disturb the generation of random numbers, then you have to basically do two different types of physical mechanisms at the same time. And then we have a mixer, which is basically a Starfish 512 that collects data from this in round robin, and then we use that to seed the Cha-Cha stream cipher. If you look at the SP800-90 standard from NIST, they basically all are using AES in this case. But we wanted to use Cha-Cha because it has a much better performance. And one of the things you can do with Cha-Cha is you can very easily sort of crank up the number of iterations you do if you want to have more security. So if the standard, if you want to do like 20 iterations, you can go like 30, 40, whatever, it just keeps going. So you can sort of, if you want to be more secure, you can actually just and drop the performance a bit. And it turns out to be a pretty good choice that we did. We can generate multi-gigabit random numbers, and we're getting, after testing, getting phenomenally good results. And this we developed on the Nalina. But we realized that, as I said, the Nalina has a lot of peripherals. We talk in CrypTech, we talk about kitchen sinks. We have a lot of peripherals and other functionality that we don't need. And if you have a lot of functionality that you don't need, most of them also normally has they're basic black boxes too, and you can really trust them. You don't even if you look in like in a microcontroller, it has a lot of interfaces like a CAN interface and a UART and whatnot. And it sits there on the bus connected to your CPU, and it's not supposed to be doing anything. But how can you actually trust that? It's not needed, and it's actually just add complexity and might actually be bad for you. So we realized that we can't base our HSM on Nalina. We need to develop something of our own. And one thing we did was we basically developed half of an HSM, the processor part, as a board with the same connector as the Nalina, and put it on the Nalina. And this one talks to the FPGA on the Nalina. So we have the design we want to have with a CPU and an FPGA, but half of it is on the Nalina and half is on the board itself. Up in the left corner you can actually see the same noise generator that we have the external noise board is now integrated into this board. So it's sort of slowly moving away from a lot of kitchen sinks and slowly moving over to our own design. And this is our pride and joy. This is what we have today. This is a board about 10 by 10 centimeters. It's basically, you can see the noise generator, external noise generator is under the hood up there. And then we have an ARM, an STM32 MCU, so it's a Cortex M4F based ARM processor, and then a pretty big FPGA under there. And that's the basic setup, right? I didn't bring my board because it's a lot of angular hairs on top of it, because I'm doing debugging on it, so I didn't want to take it out of the lab. But it's this big. And one thing that we have on this board is that we also have a small 8-bit processor, an AVR microcontroller that we can keep alive on battery, so you can actually implement the tamper protection, as we can do tamper detect in different ways, like light and somebody just open up the lid or something like that. And we have PKCS11 implemented, and we also have developed management software for it, so you can do everything you want to do with your SSM, like export keys, for example, in a secure manner, not at will, basically. And we also have today a fairly comprehensive set of FPGA cores. As I said, we have RSA, we have elliptic curve support, typically for the NIST standard curves, but we can also support the curve 5519. We have a set with Cha-Cha, AES, all the SHA cores, and also we have implemented to actually be able to do key wrap, and we think that's a first. We do key wrap in hardware, and then we have a random generator, and assorted peripherals like SPI interfaces and GPIs and stuff like that everybody has. So this is available from CrypTech today, and we use that on our board. So basically have all the complete design on SSM, and it's useful for PKCS11 applications. People are using it for DNSSEC today, for example, and as I said, we have a really good random generator, and has been extensively evaluated. One of the good things we had was Cisco. the networking company. They turned out to have a residential astronomer that does a lot of interesting computations, and he told us that you can actually get a kilowatt week in compute power from us if you want to. Because they have an interest in testing HSMs and random number generators. So they basically test every random number generator they can get hold of. And it takes about a week to run all the tests on their big compute cluster. And what they said was that we can test your random number generator for you for free on one condition, is that you don't complain when we come back to you and say it's broken. And so we can live with that. So I generate a lot of gigabytes of random data and send it to them, and they crunched for a week, and they come back and say, actually it works. Which was the first one ever outside of Cisco themselves. And that includes all of the brand HSMs that you have. So that was quite good. One thing that we're talking about openness as the FPGA development that we're doing right now is it actually requires that we use the vendor tools, Xilinx in this case. They're free as in beer, but they're of course not open. We sort of have to trust them. And they're quite complex. If the installation I have of Xilinx tool is 20 gigabytes, and that's a tool for 20 gigabytes. But all the FPGA core simulation is done using open tools, so Icarus Verilog and Verilator. The PCB design that we have was done using Altium, which is a commercial tool. We have converted. Nalina's done a great job in our project, so actually we can do the design. We can use KiCad today, and we will use KiCad for the next board. And of course, all the software is much easier. There's a lot of open tools there, so we use GCC and stuff like Klangele. And today it looks something. If you look inside of it, it's the architecture something like this. That we have the CPU on the outside, the microcontroller, and it's talking over a bus into the FPGA. And in the FPGA, we basically have a lot of co-processors as slaves to the CPU. So they don't talk to each other. It's just the microcontroller using addresses. Just say, okay, I want to do a SHA operation, for example, or I want to read a new random number from the random generator, and all those kinds. We have a key rep that actually is able to talk to the. We're going to talk about the master key memory, and then we have tamper CPU on the outside that actually can kill the key that's inside the master key memory, and then we have storage. Which is basically a flash memory. For us, there's some things with this board that we have. One thing is that bus between the FPGA and the MCU turns out to be a bottleneck. It has quite a few cycles for doing any operations, a long latency. And it's quite low capacity, 32 bits, but we can't really run it that fast. And all the cores are slaves, which means that if I would, for example, do first I want to do a hash or something, so I send all the data to the SHA core, and actually, then it generates a digest, and I have to bring that digest out of the board, out of the FPGA, and then go into the RSA core if they want to do a signing of it. So I'm moving things back and forth all the time. And that's bad for performance, also bad for security. We actually don't want to move stuff out of the FPGA if we don't really have to. A lot of cryptographic functionality is also still in the microcontroller. Particularly if we generate RSA keys, we need to do a lot of testing to see if you actually have primes. And primality testing is kind of hard to do in software. It's a lot of you read some random numbers and you sift through them, and then you decide which one you're going to use and stuff like that. So it's a lot of ifs and while and looping and ifs in the code. So it's right now better to use in the software. But that also means that secrets are exposed in the microcontroller still. And as I said, we're talking about keep the things. The STM32 microcontroller is not an open design. It has a lot of peripherals, has a lot of cool features that we don't use. And we can't really trust it that much. We actually would like to not have it there. So we can see that where the performance and security and openness can definitely be improved from what we have today. I want to talk about the thing master key memory, because it turns out that HSMs actually has black boxes inside of themselves. And the thing is this, that if you're going to do a build root of trust, particularly root of tamper response that is fast, then you want to have as little secrets that actually are very open and easy to get to as possible. So as I said, you store the keys, your private keys for example, and other sensitive information in flash memory. And what you do is that when you store them so they are protected at rest, you actually use a key wrap mechanism for that. And there's like AS key wrap, which is an RFC standard, and there's a few others ones. And so you basically encrypt your keys before you put them into the flash memory. And the key that you use to do the wrapping is called the key encryption key or master key. And this of course means that there's a single point of failure. If you lose your key encryption key, then all your secrets are worthless. They are random numbers, they're noise. And this is what they use when they actually build the tamper protection mechanisms inside an HSM. You have a single memory somewhere that can store something like 256 bits. If somebody breaks the tamper seal somehow, and you detect the tamper intrusion problem, then you try to kill those 256 bits as fast as you can. So use this single point of failure in a good way, by design, basically. And you can have the master key, the small random memory that stores the key, and the detection circuit can be powered by batteries. So the rest of the HSM can actually be powered down. So it's like the PSI, the card I showed with the supercapacitor on. That's what it does. And you can actually buy these master key memories, and they're called security managers. You can get them. That's one from Maxim, for example. Has 6 legs on it. Really small, tiny device, and it has storage for like 1 kilobit, something like that, and it has inputs to temper detection, like light sensors and movement and temperature and stuff like that. Some of the more expensive HSMs has things like a GPS inside of it. So if you try to, even if you're really careful and try to move the HSM slowly like this, it will actually kill itself. It moves out of a certain area. So that's pretty cool. And what they do is also, if you know about semiconductor, how they work, there's a problem we call remanence, that if you keep something in a RAM memory for a while, it will actually stick, particularly if you cool it down. So that what you do is if you put it into nitrogen, then you can actually keep it for basically an arbitrary long time. So one thing these security managers do is that they try to have anti-remanence protection, or imprinting is also called. Basically what they do is that they either rotate the key or inverse the bit or something like that periodically, so it actually doesn't stick. And also they work as root of trust, that there's like a private key inside of it, and you can do something like an hallmark SHA-256 pre-shared key authentication of the device. And there's a few manufacturers of these, and they of course there are formal standards, and they are evaluated by the same government agencies that evaluate the HSMs itself. And it's hard to get information. You need to get NDAs and all kinds of paperwork to get all this. So they're basically the black boxes. And we felt that, okay, we're designing an open SSM. Should we actually put a black box as where we actually keep the crown jewels in our design or not? And we decided that no, we're not going to do that. So it's having that as a fundamental part of security is not accepted for us. And as I said, right now, the master key memory is a standard serial SRAM, and our tampering is basically we kill the power to the memory. And the tamper control is a small 8-bit AVR processor outside. But we think that we can do better, and this is one of the things that I'm going to talk about right now, basically. So we have been doing this project for like 3-4 years now, and we have the board, as I showed you, and we are trying to target the things with performance and security and openness. And one thing that we've done actually is we implemented hash-based signatures for post-quantum computer resistant signature schemes. So we implemented that. That's actually available as a thing from us that we can run on our machine. You can run it on any machine if you want to, but it's kind of a differentiating thing that we can do. And we developed or developing the support for Edwards 2119 curve in hardware. So we get acceleration for that. And what we have done also is we performed an external security audit, QT53 from Germany. Did an extensive audit of our system, and there were no critical vulnerabilities. There was some vulnerabilities, and we fixed those. And one of the things that I liked was that they really appreciated the quality of the random number generator. So that's another sort of good thing was. Performance improvements. We are working on a new architecture for the RSA cores, and we think that we could probably get something like 10x or 20x performance increase from what we have today. The one we have today is quite simplistic, but it still matches some of the other, most other cores out there. But we think that we can do much better. So we also hunting latencies, particularly on the FMC bus. One of the things that was committed last night was that we actually finally are doing the NGS conversion from little to big endian inside of the FPGA instead of software. That actually took away like 4 cycles. So we can actually do memcopy now. Woo, yes! And it turns out it's actually slower than doing an unlooped version. But that gave us actually a few percent more performance. And also trying to improve basically running the FPGA at a higher clock speed. So doing some floor planning and stuff on that, so I'm working on that. Security improvements. We are trying to find ways of actually moving the crypto processing, offloading from the microcontroller into the FPGA. And I think this is a PK611 parser and management software still being running on the STM32 or something else in the future. We also tried adding a sort of a DMA engine inside the FPGA, something like the CPU can say that, okay, I want to transfer data from this core to this core, and you just do it inside the FPGA. Back and forth, a simplistic DMA, so we can eliminate transfer of data over the FMC bus to get performance, also don't expose stuff outside the FPGA. And I'm also working on the reproducible builds for releases for all of our parts, so the microcontroller and FPGA and so. And one thing I'm working on is to try to that master key memory in the security management thing. One thing I really enjoyed and was happy to see was that Clifford Wolf released a totally open FPGA design flow for Lattice ICE40 FPGAs. And these devices are based on SRAM, but they have their configuration memory flash-based inside of the same package. So basically a flash memory sitting either on top or next to the actual FPGA chip, and then you can actually do it. So you can actually put the configuration of the FPGA inside the chip, and then it's programmed, and you never have to program it again, and you don't need an external memory for it. And it is a BGA device. If you don't know BGA is a chip that has small balls under it. So when you mount it on the PCB, you basically heat it up and it will sit on the board. And one of the key things with that is that you can't get under there as easy. So it's good for security. And we think that we can do, with this design, I can actually implement basically a RAM memory inside FPGA, but I can actually implement tamper response. So I can do basically nanosecond response and basically kill the master key stored inside it in a nanosecond or so, a few nanoseconds. And I can implement imprinting and stuff like that, like the security managers, very easily. And the good thing is that I can use the open tools for this, and I can even do a audible and reproducible build of the FPGA. You can actually take the code, and you can actually see if I change this in the Verilog source code, it generates this bit in the bit stream. So you can actually trace it and see that you actually get the correct bit stream from the source code. So instead of having a black box, we actually have a very, very open and audible master key memory. And so we are looking at designing a new alpha. We're not sure about the name. There's no really good one. We're going to call it Alpha V2 MG. beta is probably not a good name for something that we think is going to be production ready. But one thing that we look at is that we try to move stuff from the microcontroller inside the FPGA. And what we had decided doing is to actually use RISC-V. So a few things I've really been so excited about in the last 2 years as the RISC-V architecture and instruction set. And it really seems to be taking off also as an open microcontroller processor core that I can use. And so we look at using some of the open ones that have been released, like Vectrix and SVRV from Western Digital. So we've actually tried to take put a microcontroller in there that can run and use the cores inside of it. And also looking at also putting a small RISC-V core, like the Pico RV32, inside of that Lattice 140, ICE40 FPGA that's going to be the master key memory. So I can actually move the tamper functionality, to detect what's inside the AVR today, into so I have basically one chip solution. And they're talking about openness improvements. So with no proprietary microcontroller, it's going to be using RISC-V. There's not going to be any kitchen sinks in there, no peripherals or weird things inside the microcontroller that we don't need. And we're doing the open master key memory and root of trust. We still use the commercial tools, but on the last CCC after Christmas 2018, there was 2 projects that are sort of related that presented new attempts of implementing open FPGA tools for something like the Xilinx Arctic 7 that we're actually using today. Really, really interesting, and it's going to be a big thing for us. And we'll see if we can help out in any ways. And we see cost and size improvements by reducing the components and removing the microcontroller and stuff like that. And we can reduce the PCB dimensions. And so we're basically going to end up having the same design as we had before, but we put the RISC-V core and the DMA as master inside of it, and we add buffers inside so we can just store data for a while at least, temporarily inside of the FPGA. And then we have the FPGA master key memory outside that keeps the main secret, and then basically everything the same. And just to end, there's one thing I'm talking about that we see that Cryptech as an open platform, and you can maybe take parts of us and assemble your own HSM to match what you need. There is 2 things that happen. One is that there's a company called Diamond Key Security that makes a Diamond SSM, and it's a commercial HSM based on Cryptech, and they actually started delivering the first machines, and they're used for DNSSEC and federal identity management. And also the Tor project, some of the core members of Cryptech is also heavily involved in Tor, and they're actually looking at taking the alpha board and changing it a little bit. One thing they need to do is actually take away a millimeter on the side of it, so it actually can fit inside of host PEC. It's 1 millimeter too big. We didn't know about that. And removing the tamper microcontroller and some of the interface chips. But basically it's the alpha board basically. And to be able to run, to do what the directive authorities in the Tor protocol is doing. So you can offloading the operations for that into the board itself. And this is what the Diamond HSM looks like. So it's, if you look inside, what they actually have is they have 2 of our alpha boards. And right now they have Raspberry Pi. They will probably, hopefully go to, and I think going to go to RISC-V as the next iteration of this one. And you can use this, and this is what they use for DNSSEC, for example. And they're available basically right now. So that's basically the Cryptech project, and I hope you can understand that we have these trying to move forward towards something that is open and trusted and not a black box. And Cryptech is sponsored and has been sponsored by a lot of organizations, and big thanks to them. And questions? So I'm done, basically.
First, I'm going to say that I am actually pretty impressed because I was like taking notes of questions and you kept answering them. So, sorry, kudos for that. But there is this one question I still have. You said that you are using ChaCha20 for the random number generator because it's faster. Which speed did you get from the ChaCha20 core as opposed to the AS core when you were trying to compare one with the other on FPGA builds?
It's running it, if you say AS256 compared to ChaCha with 20 iterations is something like hundreds of megabits compared to a number of gigabits. It's quite big faster. And the reason for that is that you have almost the same number of iterations, 20 versus 14, or actually it's going to be 16 in the AS core, because you need but the block size is much bigger in ChaCha.
You're looking at the common criteria certification also?
If we haven't designed the machine very much to be impossible to do that, and if somebody would like to do that, that would be fine with us. We would really like to see the results, but we have no plans for doing that, and I don't think that Diamond Key is planning to do that. As I said, we are using a random our what's called the DRBG part of the random the digital random bit generator, called in SP 800 terms, is ChaCha, not something like ASCTR. So we have components and parts of it that's not compatible with common criteria.
Okay, thank you.
How come you're not using LLVM instead of GCC for actual compiling?
That's a good question. I think I'm not so involved in the software part team. We've been using the LVM, at least the scan build part of it, to doing static code analysis of it. But I can't say why they exactly use just GCC in this case, or only GCC. For RISC-V, we moved that one. Hopefully the RISC-V patches for LVM is going to be in LVM, but right now it's in GCC, so for right now it'll be GCC.
Thank you.
Any more questions? Okay then. Thank you.